Good evening, everyone. So this will be the second session for the electrostatics, right? With respect to our NEET 2024, we have already done first part of the electrostatics in the first session, right? So in this session, we'll be discussing the second session, second part of the electrostatics, where we'll be discussing about some of the important questions for your upcoming NEET 2024 exam, right? Not only that, we'll be discussing some of the previous year questions as well, right? So let's begin with the question number one, right? So the question number one you can see here on your screen, right? So question number one is that a large sheet of uniform charge passes through a hypothetical sphere, right? I can see here we have a large sheet of uniform charge which passes through a hypothetical spherical surface, right? The figure shows principal section of the situation, and the electric flux through the spherical surface is given by, right? You can see here there's a large sheet, large uniform sheet, right? The charge density of this uniform sheet is given as sigma, right? Sigma is the charge density for this uniform sheet. Some part of this sheet is present inside the sphere, right? And the part of the sheet present inside the sphere will be a circular in nature, right? It will be a circular portion of the sheet present inside the sphere, right? It will be a circular portion of the sheet present inside this sphere, right? Now, the radius of that circular portion, which is present inside the sheet, let's suppose the radius of that circular portion will be from here to here. Let's suppose that's y, right? Y is the radius of the circular portion of the sheet, which is present inside the sphere, right? So we have to calculate the total flux, right? We have to calculate the total flux. We know according to Gauss law, right? We know according to Gauss law, the total flux in a closed surface. Sphere is a closed surface, right? The total flux through the closed surface is nothing. It will be equal to the total charge enclosed within the surface upon the epsilon naught, right? Upon the epsilon naught, right? Now, what we have to do is that we have just to calculate the total charge present inside this spherical surface, right? So the total charge present in this spherical surface will be the charge because of the circular portion of the sheet, right? I can see here, let's suppose from here to here, the radius of this sphere is r, right? Radius of this sphere is r, and from this point to this point, the distance is x. Then we can say that this y is nothing. This is equal to under root of r square minus x square, right? R square minus x square, and this is nothing. This is the radius of spherical portion, right? This is the radius of the circular portion inside the sphere, right? It's the radius of circular portion. It's the radius of circular portion of the sheet which is present inside the sphere, right? Which is present inside the sphere, right? Now, y is equal to under root of r square minus x square, right? Now, the total charge present inside this sphere will be the charge present in this circular portion, right? The charge density of this sheet is sigma, right? If sigma is the charge density of this sheet, then the charge of this circular portion will be nothing. It will be q is equal to charge density multiplied by the circular area of this circular portion present in this sphere, right? That will be equal to pi r square, where r will be the radius of this circular portion, right? Now r here is y, that will be y square, right? So it will be sigma pi under root of, that will be r square minus x square, right? R square minus x square. Now this amount of charge will be enclosed within this sphere, right? So therefore the net flux through this sphere will be nothing. It will be equal to the charge enclosed, that's sigma pi r square minus x square upon the epsilon naught, right? So this will be the total flux through this sphere, right? So this will be the total flux through the given sphere, right? Now let's move on to the next question, right? The question number two, right? The question number two says that a uniform electric field, right, having strength E is existing in XY plane, right, as shown in the figure, right? We have to find the potential difference between the origin O and point A, whose coordinate is given as DG0, that is D comma D comma 0, right? It lies in the XY plane, right? We have to find the potential difference between the 2 points here, origin and the point A, right? Origin and the point A, right? We know that electric field as a function of potential is nothing. That's E is equal to, that's minus dV over dr, right? Minus dV over dr, or we can write this dV as minus EdR, right? Minus EdR, right? minus E dr, right? Or this dB will be nothing, it will be minus E dot dr, right? E dot dr, right? Particularly it will be E dot dr, right? Now integrating this dV on both sides, right? We will get the potential difference between the 2 points, right? E dot dr, right? This will be the potential difference. Now the position vector of this point here, let's suppose it's the potential difference between VO and V, right? So we can write it as V minus V naught. If the potential at this A is V, V minus V naught will be the potential difference between the 2 points, delta V, right? That will be delta V. Now this will be nothing, it will be E dot dr, right? E dot dr. So we can write this as integral of electric field is E, right? E dot dr, we can write it as dx I cap, right? Dx I cap plus dy j cap, right? Dy j cap. So the length element in terms of the vector, dr vector can be written as, it's nothing, dr vector will be dx I cap plus dy j cap plus dz k cap, right? Dz k cap. Now here all the electric field and the points lie in the xy plane. So dz will be here 0, right? Dz will be here 0, right? And now integrating it with the proper limits. Now from here to here, the x is going to change. X is going to change from 0 to d, right? The y is also going to change from 0 to d, right? So the value of this potential difference will be V minus V naught. That's equal to delta V, right? That's going to be equal to minus integral of E dx with the limits 0 to with the limits. Now electric, let's suppose this angle here is theta, right? Now let's suppose that this angle here is theta, right? So it will be uh, E dx, right? E dx, right? I cap, right? We have to do dot with it, right? It will be integral of E dotted with dy j cap, right? Dy j cap, right? You can see here, you can see here. Now the angle between this x and y, we have to calculate the angle between this x and y, right? Let's suppose if it's at an angle of theta, right? If it is at an angle of theta, right? At an angle of theta, then angle between this dx vector and e vector will be theta here, right? This will be theta, right? This will be theta here, right? And then the angle between dy vector and the electric field vector, it will be 90 minus theta, right? It will be 90 minus theta, right? Now you can see here delta v will be with the limits 0 to d for this and limit 0 to d for this as well, right? 0 to d and 0 to d, right? Now uh, is a uniform electric field. It's a uniform electric field. It's having the constant direction as well as magnitude, right? So we can write it as E will be outside integral A dot dx will be ex cos theta, right? Ex cos theta with the limits E dx cos of theta, right? With the limit 0 to t, we'll be left with minus ed cos of theta, right? Minus ed cos of theta, right? Minus ed cos of theta, right? And similarly, we'll be left here with E dy. The angle between the electric field vector and the y component of this position is actually 90 minus theta. That will be cos 90 minus theta. And cos 90 minus theta is nothing. That's the sine theta, right? It means it will be nothing. It will be Ed sine 90, right? So sine theta. Cos 90 minus theta will be sine theta. So the final answer we will get here is nothing. That's minus Ed, right? Minus Ed cos theta plus sine theta, right? Cos theta plus sine theta. So this will be the potential difference between the 2 points, right? Potential difference between the 2 points O and A, right? So this is the potential difference between the 2 points O and A, right? Let's move on to the next question, right? The question says that a negative charge particle minus q comma m is revolving around a uniformly charged long wire plus lambda, right? But the speed of the particle. The question says that let's suppose we have a uniformly charged long wire, or we can say infinite wire, right? Infinite wire, right? It goes from plus infinity to minus infinity, right? The charge on this wire is given as positive charge with the charge density given as lambda. Lambda is nothing, it's the charge per unit length on this wire, right? Now at a distance of r, you can see at a distance of r from this wire, there is a charge, right, which is moving in a circular path, around this wire, right? Which is moving in a circular path around this wire. The charge is of charge q and mass is m, right? And it's very obvious that charge should be a negative charge, because then only it will be attractive force, and then only it's possible for the charge to move in a circular path. Otherwise the force would be repulsive. If the charge q is a positive charge, there will be no circular path or circular motion for this charge q, right? So charge q must be a negative charge, then only it's possible to have attractive force between the line charge and charge q, then only it's possible to have circular motion for this charge minus q, right? Now, this necessary force required for the motion of this charge q in a circular path, that's what we call a centripetal force. And this necessary centripetal force for this charge minus q is provided by the electrostatic force of attraction between the line charge and the charge q, right? Between the line charge and the charge q. So the electrostatic force of attraction here between the line charge and charge q will be nothing. It will be the charge q multiplied with the electric field at this point. We know that electric field, because of the infinite line charge at this point at a distance of r, is nothing, that's equal to E is equal to lambda upon 2 pi epsilon naught r, right? So this will be the electric field at this point because of this infinite charge density, right? Infinite charge line, right? That is lambda upon 2 pi epsilon naught r, right? So the force at this point will be nothing by magnitude, that will be q lambda upon 2 pi epsilon naught r, right? This will be the force, and this force will be the necessary centripetal force required for this particle to be in a circular motion. So it means it has to be equal to mv square upon r, right? Mv square upon r. So from here we have to calculate the speed of the particle, right? R and R will get cancelled, right? We'll be left with value of V as it will be q lambda upon 2 pi epsilon naught m under root. So this will be the value of velocity for this charge, which is moving in a circular path, right? Because of the attractive electrostatic force between the charge minus q and the infinite line charge of charge density lambda, right? So this is how we can solve this question, right? It's a very basic and fundamental question, and very basic concepts are involved in it, right? It's very easy to understand. And the first important point is that we need to understand the language of the question and the approach of the question, right? So this is how we can understand this question and approach the question to solve it, right? Now let's move on to the next question. Moving on to the next question, the question is with respect to the electric field on the axis of a ring, right? The question is that find electric field on the axis of a uniformly charged ring. We have a uniformly charged ring, right? The total charge on this ring is q, and the radius of this ring is capital R, right? We have to find the electric field on the axis of a ring at a distance x is equal to root 3r, right? It's root 3r, right? At this point, at this distance, we have to find at a distance x equal to root 3r. We have to find the electrostatic field, right? Now let's try to find it, right? The electrostatic field at this point, we know the electrostatic field because of the ring on the axis of a ring. It's nothing, it's given by the k times charge on the ring x upon under root of r square, where r is the radius of the ring, x square to the power 3 by 2, right? So this is the electric field at this point P, and it has to be towards this point P, or we can see it's away from the center of the ring and along the axis of the ring. This is the direction of the electric field because of the ring having the charge plus q, right, and radius r. Kqx upon r square plus x square to the power 3 by 2 will be the net field at this point P because of this uniformly charged ring, right? Now we have to calculate this field at x equal to root 3r. We'll just substitute the value of x equal to root 3r in this equation. We'll get to know about the electric field at this point, right? That will be x is root 3r upon r square. X square will be x square has to be equal to, right? Okay, x is root 3r, right? X square has to be equal to, it will be 3r square, right? 3r square to the power 3 by 2, right? 3 by 2. And from here, it will be kq root 3r, right? 3r square plus 3r square, it will be 4r square, or we can write it as 2r whole square multiplied by 3 by 2, right? From here, 2 and 2 will get cancelled. So the net field here will be root 3 kqr upon, we will left with 2r whole cube. It will be nothing. It will be 8r cube, right? From here, r and r will cancel. We'll be left with the square, that is root 3 over 8, right? K cube upon r square. So this will be the net electrostatic field because of this charge ring at a distance of root 3r. It's a direct formula based question, nothing special in it, right? So let's move on to the next question, right? Now it's a very important question with respect to your upcoming NEET exam. That's the electric dipole moment of the given arrangement, right? We have to find the electric dipole moment, right? The electric dipole moment for any discrete charge distribution, electric dipole moment for any discrete charge distribution with respect to with respect to a given reference or with respect to a particular origin, right? That's given by the net dipole moment is nothing. It is actually equal to, for the discrete charge distribution, it is summation of qi ri vector, right? It's summation of qi ri vector. So this is the net electric dipole moment, right? It's nothing. It's the summation of qi ri vector, right? Qi ri vector. Now we can apply this equation. Let's suppose case number second, right? Case number second. Now we can find the dipole moment in the vector form. Dipole moment in the vector form, right? Let's suppose this is the origin. This is the origin, right? If this is the origin, then distance from here to here, it will be nothing. It will be li cap, right? We can write this vector as li cap. So the r vector for this charge q will be li cap, and r vector for this charge q will be lj cap, right? Now, we'll be applying the calculating the net dipole moment. That's summation of qi ri vector, right? Ri vector. I can see the charge which is at origin, its position vector is a null vector, right? It's a null vector because it's itself a charge at the origin, right? So because of this, dipole moment will be equal to 0, right? Now, because of this charge q, the charge is q, right? And the vector is li vector, right? It's li vector. And because of this charge plus q, the charge is q, and the vector of this position vector of this charge q with respect to this origin is lj cap. So it will be lj cap, right? So this will be the net dipole moment, right? So calculating the magnitude of this dipole moment, it will be under root of ql whole square plus ql whole square, right? So it will be nothing. It will be root 2 times q multiplied by L. So this will be the net dipole moment because of this charge distribution. For the part second, right? For the part second. Another way of calculating this dipole moment is nothing. Let's suppose another way is to calculate this dipole moment or the magnitude of the dipole moment is that. Let's suppose we have the two charges minus q and minus q. We know the direction of the dipole moment is from negative charge to the positive charge. Because of this minus q and plus q, the dipole moment will be along this direction, right? And because of this minus q and plus q, the dipole moment will be along this direction, right? So dipole moment because of these two will be q into L, and because of these two it will be q into L, right? So both these dipole moments will be perpendicular to each other. That's P1 and this is P2 having the equal magnitude. So their resultant will be along this direction, right? This is the net dipole moment here. That will be nothing. That will be under root of QL whole square plus QL whole square, right? So from here it will be nothing. It will be root 2 Q multiplied by L, right? Root 2 q multiplied by L. So this is another way of calculating this dipole moment here, right? Now, talking about the part one here, right? For the part one, we'll once again do the same thing. We'll distribute these charges minus q minus q. One dipole moment will be along this direction. Another dipole moment will be along this direction. Let's suppose this is P1 and this is P2. Both these dipole moments are at an angle of 60 degree, right? P2 is nothing. It's q into L, and P1 is also q into L, right? These are the two vectors. These are the two vectors at an angle of 60 degree with respect to each other. So their net dipole moment will be equal to P net will be nothing. It will be 2 times QL cos 60 upon 2, right? Cos 60 upon 2, because these are the two vectors of equal magnitude at an angle of theta, where theta is 60 degrees. So their net dipole moment will be QL cos 60 upon 2 is root 3 over 2, right? Root 3 over 2, 2 and 2 will get cancelled. We'll get the net dipole moment here, root 3 Q multiplied by L for this case, right? Root 3 Q multiplied by L will be the net dipole moment for the arrangement first, right? In general, for the discrete system, this is the equation, right, to be used for calculation of the. It will give us the net dipole moment in the vector form, right? It will give us the net dipole moment in the vector form, right? This is how we can calculate the dipole moment in vector form for a discrete charge system, right? Now let's talk about this question, right? Let's talk about this question. The question says that a thin disk, right? The question says that a thin disk of area 2 meter square right? A thin disk of area 2 meters square is placed in xy plane, right? In a uniform field of strength E is equal to 2 I cap minus j cap plus 4 k cap, right? So we have a thin disk of area 2 meters square which is placed in xy plane, right? Which is placed in xy plane, right? Which is placed in xy plane. So the disk is actually placed in xy plane, right? Okay, it's placed in xy plane. So this disk is placed in xy plane like this, right? In this plane, the disk is placed, right? Let's suppose this is the z direction. This is the z direction, right? This is y, this is x, and this is z, right? So in this plane, xy plane, the disk is placed, right? The area of this disk is given as 2 meters square, right? 2 meters square. And the electric field is a uniform electric field, that's 2I cap minus j cap plus 4k cap. Find the flux of the field passing through the disk, right? We have to find the flux through the disk, right? Now you can see here, there are three components of the electric field. One is the x component, another is the y component, and third one is the z component, right? The direction of the area vector of this disk is nothing. It's along z direction. It's along z direction. It's parallel to the z direction, z axis, or y. We can say the unit vector of this area vector associated with this disk is k cap, right? Is k cap, right? Now it means that the flux because of the x component and y component because of this electric field has to be zero, because x component and y component electric field will not penetrate into the disk, right? So the flux because of this x component of this electric field and the y component of this electric field will be zero, because area vector is directed along z direction, right? So the only flux here will be because of the k component, right? K component, right? And we know that the net flux because of uniform field will be nothing, E dot A vector, right? E dot A vector. So E is nothing, that's 2I cap minus j cap plus 4k cap, right? Now dotted with the area of this disk is 2 along the direction of k cap, right? So the net flux through it will be nothing, it will be 8, right? It will be 8, right? 8 will be the net flux passing through this disk, right? So the unit of this flux will be, it will be volt meter, right? It will be voltmeter. It will be voltmeter. So this is the SI unit of the flux, right? Now let's move on to the next question, right? The next similar question here. A uniform magnetic field, sorry, a uniform electric field is equal to 2 I cap plus 10 I cap plus 4 J cap volt per meter is present in space. Find out flux passing through the area of 10 meters square if it lies in xy plane, xz plane, yz plane, right? It's once again the same similar question, right? Similar question to some extent. It's the similar question, right? YXZ, right? YXZ, this is the Cartesian system, right? Now we are placing there is some area of, there is some loop, we can say, of area 10 meters square, right? And it is placed in different planes in different three cases, right? First of all, it is placed in xy plane. Let's suppose if we place this loop in xy plane, right? If this loop is placed in xy plane, then what's going to happen is that the direction of this area vector will be along, it will be along k cap direction, right? It will be along k cap direction, right? It has to be along k cap direction, right? Then the flux because of this case first, in this case first, the flux through this loop will be nothing, it will be E dot A, right? It will be E dot A, that will be equal to 10 I cap plus 5 j cap dotted with dot product with, and the area of this loop is 10, right, with the direction k cap, right? K cap. So the net flux through this will be nothing, it will be 50, right? It will be 50 voltmeter, right? So this will be the net flux through this disk, right? The third case is that if we place this disk now, if we place this disk along xz plane, right? We are placing this disk along xz plane. It means that we are placing this disk in this plane right now, because this is y, this is z, and this is x. Now it's placed in a xz plane. If this disk is placed in xz plane, so the direction of the unit vector of this disk, or the area vector of this disk, will be along j cap direction, right? So the net flux in this case second, will be, that will be E dot A, right? E dot A, right? It will be 10 I cap plus 5 j cap, right? Dotted with 10 j cap, right? 10 j cap. So from here, the net flux here will be 100 voltmeter, right? So this will be the net flux in the second case. For the third case here, right? For the third case here, you can see here, if we have the third case, for the third case here, this is y, this is x, and this is z. Now it's placed in yz plane, right? If this is placed in yz plane, it means the disk has to be along in this plane, right? The disk is in this plane, that's in yz plane, right? The disk is in yz plane, then the vector or the area vector will be along, it will be along I cap direction, right? I cap direction. So the total flux will be here in this case. The total flux now here in the case first, you can see in the case first, the area vector is along k cap direction, right? But there is no component of electric field, no component of electric field along k cap direction. It's only I cap and j cap direction, right? So you can correct it here, right? There is no component, there is a zero component along k cap direction. So the flux in the first situation has to be zero, right? The flux in the case one will be zero flux, right? So in the first case, the flux through the disk through the loop will be zero, right? In the third case, now its area vector is along I cap direction, right? It's along I cap direction, right? The electric field is given as the flux will be E dot A, right? The electric field is 10 I cap, 10 I cap plus 5 J cap, right? Now dotted with this area vector, that will be 10 I cap, right? 10 I cap, right? That will be 10 I cap, right? Now here it will be 10 dot 10, it has to be 50, not 100, it has to be 50 voltmeter, right? So 10 multiplied by 5 will be 50. Now here this will be 10 multiplied by 10, that's equal to 100 voltmeter. So this will be the net flux in the case third, right? 100 voltmeter will be the net flux in the third case, right? So it's important to know about the direction of an area vector. That's very important before calculating the flux in the vector form, right? If the electric field is given in the vector form, right? For particularly a uniform electric field, right? So that's how we can calculate the flux for different cases, right? It's very important to know the direction, to know about the direction of a area, right? Or area vector which is associated with a given area. Right? Then only we can dot it with the electric field to calculate the total flux through the given area, right? Now let's move on to the next question, right? The question is that a hemispherical shell of radius r is placed in a uniform field as shown in figure, right? Find the flux through the hemisphere. Find the flux through the hemisphere, right? Now you can see there's no charge enclosed in this hemisphere, right? There's no charge enclosed in this hemisphere, or we can say the charge enclosed by this sphere is equal to zero, right? We can use the Gauss law, right? We can use the Gauss law. So the Gauss law says that uh, if the charge enclosed is equal to zero, right? Then total flux through the surface has to be equal to zero because the total charge enclosed is zero, right? If the total charge enclosed is zero, the total flux will be zero here, right? It will be zero flux, right? I can see here, you can see here that there are two areas for this hemispherical bowl, right? One is the curved surface area, right? Curved surface area, and this is the circular area, right? This is the circular portion, right? Now we can see here for different at different points the direction of this covered surface area is different, right? Different, so it will be difficult to find the flux through this covered surface area. But what we'll be doing is that if we talk about the total flux, right? So phi total will be equal to zero, right? Total flux will be equal to zero, right? There's no doubt in it. The total flux will be equal to zero, right? But let's suppose the total flux entering, the flux entering through this covered surface area, right? So we can say flux entering and flux plus flux leaving has to be equal to zero here, right? In this case, right? Now flux is entering from the covered surface portion for this sphere, right? But we have to calculate the flux through the circular portion also, right? If we calculate the flux through the circular portion, the direction of this area vector will be along the direction of the electric field vector, right? Along the direction of the electric field vector, right? So the total flux through the circular portion will be, it will be the flux leaving, that will be equal to flux entering plus flux leaving, that will be electric field multiplied with the area, that has to be equal to zero. Or we can say the flux entering the sphere is actually equal to minus EA, right? So this is the flux entering the sphere, that will be minus E pi r square, right? So this is the total flux entering the sphere, so total flux entering the sphere, right? And the total flux leaving the sphere is EA, but the total flux through the whole sphere, right? That has to be equal to zero, right? The total flux will be zero, right? Now let's find out the flux because of this charge placed at one of the faces of a cube, right? The charge has been placed at the center of one of the faces of a cube. We have to find the flux through the cube, right? What we can do here is that, let's suppose if we construct an imaginary cube here, right? Imaginary cube like this, right? If we construct an imaginary cube, right? Identical cube, another identical cube like this, right? So if another identical cube is constructed here, right? So this is another identical cube constructed here, right? Now you can see here the charge is now placed at the center of the two cubes, right? It means that the electric field lines will be equally distributed among the two cubes, right? It will be equally distributed among the two cubes, right? It will be equally distributed among the two cubes, right? So the total flux through this sphere will be equal to Q upon epsilon naught, right? The total flux through this closed surface will be Q upon epsilon naught. But this flux has to be distributed equally between the two cubes. It means flux through each cube will be nothing. It will be Q upon 2 epsilon naught, right? It will be 2 upon Q epsilon naught. So the net flux through the cube will be nothing. It will be Q upon 2 epsilon naught, right? This will be the flux through the cube. Now the similar situation here, right? Similar question here, right? The question is that find total flux through cube and flux through each face of the cube, right? The total flux through the cube we have to calculate, right? Now let's suppose that we can just say that if we construct 7 more cubes on this cube, right, making it a bigger cube, right, making it a more bigger cube, right, then you can see here this charge appears to be at the center of the 8 cubes, right, at the center of the 8 cubes, where the larger cube is made up of 8 small cubes, right? 8 small cubes, right? I can see here the flux through each cube will be nothing. The flux through the whole cube will be phi. Through the whole cube will be the charge enclosed upon the epsilon naught. But you can see here the flux through each cube. Now it is connected with the 8 different cubes, right? 8 different cubes. You can see this is 1, this is 2, this is 3, this is 4, right? This is 5, this is 6, this is 7, and there will be the 8th cube, right? There are 8 cubes. Now the flux is at the center of this cube. It means the flux will be distributed equally in each and every cube, right? So flux through each cube will be nothing. It will be Q upon 8 epsilon naught, right? So Q upon 8 epsilon naught will be the flux through each cube. So flux through each cube will be 8 Q upon 8 epsilon naught, right? So the flux through this cube will also be Q upon 8 epsilon naught, right? Q upon 8 epsilon naught. Now, but what we have to calculate is that we have to calculate the flux through each face as well. Flux through each face as well. Now let's focus on this cube, right? Now you can see that charge is placed at this point, right? Now there are 3 faces through which the flux will be 0, right? There will be no electric field penetrating through those faces. This will be the phase number 1, right? This is the phase number 2, and this is the phase number 3, through which the no flux will be entering the phases, right? Or we can say the flux through 3 phases when charge is placed at one of the corners is 0. Flux through 3 phases is 0, and the flux is only distributed passing through 3 phases only. The total flux through the cube here in this situation is Q upon 8 epsilon naught, and this flux is only associated with the 3 faces of the cube, right? The total flux through this cube is Q upon 8 epsilon naught, and that flux too is also associated with only 3 faces of this cube. It means the flux through each face will be nothing. It will be the flux through the cube is 8 upon epsilon naught divided by the 3, right? Because the flux is only distributed among the 3 faces. The total flux through each face will be Q upon 24 epsilon naught, right? Q upon 24 epsilon naught, right? So this will be the flux through the each face, right? And flux through the cube, right? Now let's discuss a conducting sphere, right? Conducting sphere, right? And the potential due to the conducting sphere inside and outside, right? We know that the potential due to a sphere is outside the sphere is same as that of the potential of the point charge, right? The electric field outside the sphere is same as that of the point charge, right? But the electric field is different for the sphere inside, and potential is different for the sphere inside, right? A conducting sphere of radius r has charge q. Find the potential at distance of r by 2 and 3r by 2 from center, right? If it is a conducting sphere, right? If it is a conducting sphere, so whole charge is going to reside on its surface. So whole charge is going to reside on its surface, right? The whole charge will reside on the surface of this sphere, right? but we have to find the potential at two different points. One is inside r by 2, right, at a distance of r by 2, and the second point is at a distance of 3r by 2 from the center of this sphere. Let's suppose this is r by 2 distance and this is outside point at a distance of 3r by 2. So these are the 2 points at which we have to find the potential, right? Now you can see here inside the sphere, there inside the conducting sphere, the charge does not reside inside the sphere. The whole charge resides on the surface of the sphere. So the potential on the surface of the sphere has to be the potential inside the sphere, right? The potential at r by 2 will be the potential on the surface, right? That will be potential on the surface, and we know the potential on the surface of a sphere is the potential, same potential as that of a point charge, right? That will be k q upon r, right? This is the potential on the surface of this sphere, right? But outside, also the potential is same as that of a point charge for a sphere, right? For a sphere, the potential is same as that of a point charge, right? Or for the outside point, right? Therefore, we can say at this from the at a distance of 3r by 2, the potential at a distance of 3r by 2 will be kq over r, where r is nothing, that is 3r over 2, right? So the net potential at this point p will be 2kq upon 3r. So this will be the net potential at this point p, right? So at inside point, the potential on the surface will be same if this is a conducting sphere, because the charge will reside on the surface of the sphere. If the non-conducting sphere is there, then the total charge will be different. Total potential inside the sphere will be different than the surface, right? And now let's discuss this question, right? There are three concentric shells, right? Three concentric shells. Each of these shells are having charge Q1, Q2, Q3, right? That shell with charge Q1 has radius A, then there is second shell with radius B and charge Q2, third shell with radius C with charge Q3. We have to find the potential at points A, B, C, and D due to the given arrangement, right? We have to find the potential at the points A, B, C, D because of the given charge distribution, right? Or because of the given arrangement. Let's first of all focus on the point A, right? Let's try to find out the potential at the point A. At the point A is this common center for all the three concentric spherical shells, right? We know that potential, if it's a conductor, that the potential on the surface of the shell has to be in, the potential inside, because the electric field inside the shell does not exist. It is equal to 0, right? For a conductor, right? For a conductor. Now you can see here, there is a Q1 charge on this conductor, Q2 in the second conductor, and Q3 on the third conductor, right? Now point A is the inside point for this, is the inside point for this conductor, right? For conductor A, right? For the first conductor, it's an inside point. It means the potential because of the charge Q1 will be the same potential as on the surface of conductor 1. That will be KQ1 upon A, right? KQ1 upon A. For second shell also, this point is inside point. So the potential will be KQ2 upon the radius. That will be equal to B, right? And the third, because of this shell, it will be KQ3 upon the radius, that's C, right? That's C. So the net potential will be here KQ1 by A plus KQ2 by B plus KQ3 by C, right? This is the potential at this point A, right? For point A. Now talking about the potential at point B. Point B. Now you can see here the point B for the first inside sphere, for the first sphere, the potential point B is on the surface of the first sphere, right? The potential because of this Q1 charge will be nothing, KQ1 upon the radius of this sphere, that will be A, right? But for the second sphere, B is once again an inside point for this second shell. It will be, the potential will be KQ2 upon B, right? And for this third spherical shell also, it's B is an inside point. KQ3 upon C will be the potential, right? So you can see here once again it's KQ1 upon A, KQ2 upon B plus KQ3 upon C, right? It's the same potential, right? Now let's talk about the point. Let's talk about the point C, right? Point C. Now point C, right? Now let's focus on the point C. The point C is for the first sphere. For the sphere of radius A, the point C lies outside the sphere, right? The point C lies outside the sphere. The potential because of this Q1 charge will be KQ1 upon, now it lies at a distance of B. It will be KQ1 upon B, right? Because of the charge Q1. And because of the charge Q2, it will be KQ2 upon B because it's on the surface of the charge Q2, right? Now, for the third shell, the potential point C lies now inside this third shell, right? So the potential because of Q3 charge will be KQ3 upon C, right? So this will be the net potential at point C, right? This will be the net potential at point C, right? But let's focus on the point D. On the point D, you can see here at point D, the net potential, this point D lies outside the first sphere and the second sphere as well, and it lies on the surface of the third sphere. So because of the first sphere, it will be, the potential will be KQ1 upon C, and because of the second sphere, the potential will be, it lies at a distance of C, right? It will be KQ2 upon C, right? And for the third sphere, it will be KQ3 upon C, right? It means the net potential will be K upon C multiplied by Q1 plus Q2 plus Q3, right? So this will be the net potential at the point P, at the point D, right? So this is how we can actually calculate the net potential at different arrangements. The concept is that if the point lies inside the particular shell, the potential will be the same as that on the surface, right? If the point lies outside the particular shell, the potential will be like a point charge at a distance of R, right? Now, let's discuss this question, right? Find V inside minus V out for the given arrangement of shells, right? It means that we have to find the potential difference between which points, right? Okay, we have to find the potential difference between this point. Let me call this as point A and let me call this as point B, right? So we have to find the potential difference between VA and VB, right? Now, first of all, we'll find the potential at B. For A point, the potential will be, now this point A will lie inside this Q1 sphere, right? It will be the potential equal to KQ1 upon A, right? For the second sphere also, it's inside the sphere, that will be KQ2 upon P. This is the potential at A, right? Similarly, potential at B will be, the potential at B, the point B will lie outside the first sphere, right? So the potential at B will be KQ1 upon P plus, and it lies on the surface of the second shell, right? That will be KQ2 upon P, right? KQ2 upon P. Now, calculating the potential difference between them, that will be equal to KQ1 upon A plus KQ2 upon B, right? Minus KQ1, KQ1 upon P minus KQ2 upon P, right? Now, from this and this will get cancelled, right? We'll be left with KQ1 1 upon A minus 1 upon B. So this will be the potential difference between the 2 points, right? This will be the potential difference between the 2 points, right? Well, let's discuss this third case here, right? The third case is that now in this case we have to find the electric field, not the electric potential, right? The two concentric conducting spherical shells are shown in figure, right? We have two concentric spherical shells shown in figure, right? Find electric fields at points 1, 2, and 3. We have to find the electric field at points 1, 2, and 3, right? There are 3 points. This is point 1, this is point 2, and this is point 3. We have to find the electric field at these points. Now let's try to find out the electric field, right? You can see here, this point 3 lies inside the conductor, right? We know that inside a conductor, the electric field is zero, right? Because it's a space of constant potential, right? So the electric field inside the conductor or metallic surface has to be equal to zero. We can see the electric field at E3 has to be equal to zero, right? So E3 will be a zero, right? Now, since inside shell has a charge of plus Q1, right? It's a metallic conductor, right? Conducting shells, right? Then this shell will induce a minus Q1 charge on this surface, right? And plus Q1 charge will be induced here, right? Plus Q1 charge will be induced here, right? Now let's talk about this charge point 2, right? We know E3 is equal to 0. For point 2, if we draw a Gaussian surface, right? If we draw a Gaussian surface for point 2, right? This is the Gaussian surface. Let's suppose it's at a distance of R2, right? Then the charge enclosed will be nothing. It will be the charge Q1 only, right? It will be charge Q1, right? It will be charge Q1. We know for the spherical symmetry, the electric field is nothing. It's Q enclosed upon 4 pi epsilon naught R square, right? 4 pi epsilon naught R square. The charge enclosed here is nothing. It's Q1 charge. So the net field will be Q1 upon 4 pi epsilon naught R2 square. This will be the electric field at this point 2, right? This will be the electric field at this point 2. Now let's calculate the electric field because at this point 1, right? We have to find the electric field at point 1, right? At point 1. So the net charge here comes out to be equal to, right? If this is for inside a surface, the charge induced will be minus q, and for the outside surface, the charge induced will be plus q1, right? It will be plus q1, right? So it means that the net charge on the outer surface of the sphere will be q1 plus q2, right? It will be q1 plus q2, and we know for outside region for a sphere, the electric field is nothing. It's like a point charge, right? So for point 1, the net electric field at 1 will be nothing. It will be like a point charge, that is k q1 plus q2, right? Upon the distance square, that will be r1 square, right? This will be the electric field at point 1, right? So E1 will be k q1 plus q2 upon r1 square. So E2 will be equal to q1 upon 4 pi epsilon naught r2 square, and the electric field at point 3 will be 0, right? So this is how we can find the electric field at different points in a concentric shells, right? Now let's look at this question, that question as a function of x and y and z. That's v is x square y plus y square x z, right? Plus 5. Then we have to find the electric field at point 110, right? We know electric field is nothing. It's the negative gradient of the potential, right? Negative gradient of the potential, right? And the gradient here is nothing. That's del upon del x of I cap, right? Plus del upon del y j cap, right? Plus del upon del z k cap, right? These are the partial derivatives, right? With a potential v, right? Now the value of, or we can say ex here will be nothing. It will be del v upon del x, right? Minus del v upon del x, and ey will be minus del v upon del y, and ez will be here minus del v upon del z. So the value of ex here will be now we have to take the derivative with respect to x, right? Assuming taking all other variables as a constant here, right? That's x square y plus y square xz, right? That will be equal to, now we can treat y and z as constant and taking a derivative with respect to x only, right? So that will be minus 2xy, right? Plus y square z, right? Plus y square z. That will be ex, right? Now add points 1 comma 1 comma 0, right? Add points 1 comma 1 comma 0. So we'll be left with minus 2 I cap, right? Minus 2 I cap will be the value of ex, right? Similarly, ey here will be minus del upon del y of x square y plus y square xz. That will be equal to minus x square, right? Minus 2y xz, right? At a point 110, right? 110. Now for z equal to 0, this term will vanish, right? We'll be left with minus j cap only, right? So it will be minus x square, yes, only minus x square, that is minus j cap, right? So Ez here will be equal to minus del v upon del z, that's equal to minus del upon del z of x square y plus y square xz, right? Now you can see here, taking the derivative with respect to z, this is a constant here, right? This term is a constant, so its derivative will be 0 because there is no z involved here in this term, right? So we'll be just taking the derivative of this term, will be left with minus xy square, right? At a point 110, right? 110. So it means that we'll have the value here equal to minus k cap, right? Minus k cap. So the finally the net electric field at this point will be E vector, that's equal to minus 2I cap minus j cap minus k cap. This is the net electric field. So the magnitude of this electric field will be nothing. It will be under root of 2 square plus 1 square plus 1 square. That's root 6, right? So root 6 volt per meter. This will be the net electric field at point 110, right? That's how we can calculate the net electric field at a given point using the partial derivatives, right? So that's it for today's session, right? Electrostatics part second is finished. We'll be starting with the electrostatics part third. Here we'll be discussing about the capacitors, right? That will be done in the next section, right? Till then, take care and goodbye.